Hello and welcome back to this final session of the gas chapter. To be honest with you, this last chapter is going to be a lot of review from the very first few chapters we have done. However, there will be several new things that are very important and really kind of close up this chapter of gases. So again, there are definitely some things that I need you to pay attention to. I need you to grasp the concept of. All right. One of the things that I haven't really gone deep into, but I have, is the kinetic molecular theory. And again, that's why it says back to the kinetic molecular theory. Remember, there in this list there are four things that we have. Now, the one thing that I want to hit on that I have not hit on earlier is the fact is what is this theory explaining? The theory is explaining something we call an ideal gas. Okay. Now remember, ideal gases are gases that fit the kinetic molecular theory perfectly, which means they adhere to every single one of these assumptions that you see before you. Okay, very, very, very important. And I'm actually going to get you to add, let's add a fifth one in terms of it is also one of the kinetic molecular theories, okay? So let's go through this. Hopefully this will not be too long of a lecture, again, because a lot of it is review. All right, number one, all particles are in constant random motion. Check. That is true. We know that. All collisions between particles. Now, the one other thing that you need to understand is it's not just between the particles, it's also between the particles and the container wall. You have to keep that in mind as well. And then, this is the part that gets us in trouble. This idea that it says it's perfectly elastic. Now, when you think of elastic, again, you think of a rubber band, but it's not like a rubber band. It's in terms of there's no kinetic energy lost. That's what I need you to add right here beside perfectly elastic. Again, I'm just kind of cramming this in. No KE lost. So again, the example that I gave you was like playing wall ball and throwing that ball up against the wall and no energy was lost. It would be coming back exactly at the same velocity at which you threw it. Again, that's not true. That does not happen. So number two is one of the flaws of the kinetic molecular theory. All right? The volume of the particles in a gas is negligible. All this means is that they are far apart. That's all that means is they are spread out and all of those molecules are really, really, really far apart. That is true. So 3 checks off to be true as well. Number 4, and I have explained this time and time again throughout this entire lecture, so it's something that you should know by this point. The average kinetic energy is its Kelvin temperature. So they are directly related. So when your temperature goes up, your energy goes up. Okay? All right, now, the fifth one that we want to add is kind of in the bottom box. So I do want you to add it. Basically, there are no IMFs. Now, I know that it can get a lot more complicated than that. It can get a lot more scientific. But again, the kinetic molecular states that there are no intermolecular attractive forces. We know that this one is also a huge flaw because it's kind of like the example I gave earlier, I think, and whenever we were looking at this, is that if there's a school of 1,200 students, you've got to at least think one person in that entire school has to be attractive, okay? So again, that's kind of what we're saying, so that is a flaw. In the box, let's go there. This neglects any intermolecular forces as well. That's kind of what we were talking about. Gases expand to fill their containers. Solids and liquids do not. And imagine this. This is the kind of the example that I want you to understand. Imagine if you were blowing up a balloon, but when you started blowing that balloon up, only half of it expanded. The other half just stayed a saggy, uninflated balloon. Just doesn't make a whole lot of sense, okay? So that's what it means when it says to fill their container. And then finally, gases are compressible. Solids and liquids are not appreciable compressible. And you can compress them, but it's not going to make a big difference. And the only little fact that I want you to add to this is since they are compressible, that means that they can be under pressure. That's the key. And we know things that are under pressure, your colognes, your perfumes, anything that you spray that comes out in a rapid fashion because it's under pressure means it has been compressible, if you will, okay? The next one, This is extremely important, and I have been begging and begging and begging in terms of you to understand this. At the same conditions of temperature, all gases have the same kinetic energy. One more time, please grasp this idea. Please, please, please. Same temperature means same energy. All right, well, let's pretend for just a second that we're going to take this brick wall, okay? We're going to take this brick wall, and we're going to take a Hummer, okay? Again, these big old Hummers. And we're going to drive this Hummer into this wall. And then we're going to take a Ferrari. Okay, I know. Perfect artists, beautiful cars. And then we're going to drive that Ferrari into that exact same wall. Now, let's pretend for just a second that the Hummer is only going 30 miles per hour, and then the Ferrari is going 60 miles per hour. And then let's compare the masses. We know the Hummer is more massive than the Ferrari is. Well, what I'm trying to get you to understand is that your mass and your velocity are inversely related. The higher the mass, the slower the velocity. However, the lighter the mass, the higher the velocity. But here's the idea that I'm trying to get. If you can mathematically determine the ratio of mass to velocity, and you drove those two things into a brick wall at their correct ratio of mass to velocity, they would produce the exact same impact in terms of energy. One more time. Even though the Hummer is more massive, it's traveling slower, and even though the Ferrari is lighter and it's traveling faster, if they are at their correct mass to velocity ratio, they will hit this wall with the exact same amount of energy. Okay? That's kind of where I'm getting with this. That's what I want you to understand, is that no matter the molecule, as long as they're at the same temperature, they'll have the same energy. Very, very, very important for you to grasp that concept. All right? Kelvin temperature is not an index of random motion. Kelvin temperature is an index of the random motion of gases, which essentially means the kinetic energy. And again, this is the energy R. So if you're ever having to use anything with joules and energy, make sure you know this R. This is not, I repeat, this is not the Pivnert R. This is not the Pivnert R. Please do not use this R for Pivnert. This is only for joules. It's only for energy. All right, and again, here's one of your formulas, but you do not have to use it there. The kinetic energies of gas particles. The distinction between kinetic energy and speed is important. You must be careful to avoid confusing the two, because the kinetic energies of a particle does not depend upon the mass. The kinetic energy depends upon both the speed and the mass. One more time. Hopefully you caught this. Kinetic energy of particles does not depend upon the mass, but it does depend upon the mass and the speed. And here's the idea that I kind of want you to grasp. And again, I just explained it a second ago. At the same, let's try this again. At the same temperature, eventually I'll stop doing that. At the same temperature, lighter particles have greater average speed, but again, just like it says, the same kinetic energy. Yes, lighter goes faster, but they'll have the same energy as the larger particles, the more massive particles, as long as they're at the same temperature. All right, ideal gas law, again, just kind of showing this. Temperature and volume or pressure is held constant. You increase the number of particles at the same temperature, you would cause more pressure. Read that one more time. If you increase the number of particles, which means N goes up, cause the pressure to increase. So your pressure Again, why is this important? You have more collisions. Okay? Again, that is why you have more collisions. All right? And again, that's what's going to happen there. Dalton's law, again, if you want to go back and watch that in the previous video, the pressure is exerted by a mixture of gases. Again, when you're breathing, you're not breathing in just oxygen. There's nitrogen, there's hydrogen, there's carbon dioxide, there's everything going on. But the pressure is the sum of all of those gases mixed together. Okay, one more time. The pressure is the sum of the mixture of gases. And those specific mixtures have what we call partial pressures. All right. Since the gas and particles are acting independent of each other, and the volumes of the individual particles do not matter. So it does not matter what kind of space they're taking up, but the pressures will. All right, distribution of molecular speeds. Plot the number of gas molecules having various speeds versus the speed, and you get a curve. Basically what that means, the number of molecules versus speed. The more molecules you have, the higher the speed over a certain amount of time. Changing the temperature affects the shape of the curve, not the area beneath it. All right, so this is what we're getting into, and again, we're going to kind of cover that to more details in just 1 second. I think my slides are a little bit out of order, is the reason why I say that. The root mean square velocity. This is a formula that, again, I do not have the formula sheet in front of me. I do not know if it is on the test any longer. However, I do want to kind of cover it and show you what it means. Basically, what this means is you can find out the velocity of a particle if you know the formulas, if you know its molar mass based on this formula. Again, root mean square velocity. You can determine how fast it's going by this formula. All right. I do need you to know the unit of this thing. And again, the unit for velocity is meters per second. All right, that's kind of all you have to get into there. I do want to point something out, and it's this 3. Guys, I'm going to be honest with you. I don't know the true meaning of where the 3 comes from. There's way too much science behind it. Just accept it for a fact. Use this on the formula sheet if it's available. And again, I do not quite know if it's on there or not, so you may have to use it, you may not have to use it. But if you need it, it's there. Use the energy R. That is another big key. All right, so let me erase this. This R is the energy R. Now, why is it the energy R? Well, the reason is because we're talking about velocity. Velocity carries a certain amount of energy. We're not talking about pressures. Okay. Well, the other R is Latham over mole. Well, we need velocity. Velocity is energy. You're going to need a joules unit. All right. So again, make sure. Oh, if I would read very carefully, I would have seen that it says not on the equation sheet. So again, this has been updated for the new version. So again, they're either going to have to give you this or you're going to have to work around it. Okay. Since it's not on the equation sheet, I'm not going to work it for you, but I will point out a very few small things. Calculate the root mean square velocity for the helium of gases. Again, it's 3RT. Again, change your temperature to Kelvin, so we have 298. What R are you going to use? Hopefully you just said the energy R, and then helium. Well, the molar mass of helium is something very important. And I'm going to write this, and you're like, whoa, 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 what are you doing? Sorry, let's try this so it'll make more sense. It is 0.004 kilograms per mole. And I know exactly what you're thinking. Why in the world did you just put it in kilograms? All right. Well, there's a reason. The kinetic energy, and we've already seen this formula, is equal to 1/2 mv squared. This m is mass. The unit for mass is the kilogram. So why in the world does it matter that we're in kilograms? And why do we use kilograms? Again, this goes back to the fundamental unit that 1 gram is way too small to be a sufficient unit, so we use the kilograms. So how does that connect into the fact that we need kilograms instead of using grams? Well, here's another reason. we've already established that the fact that the R value is 8.31 joules per mole. Now, this is what you need to understand. And this is something that it's more of a physics approach than it is anything. I can explain it, but there's no reason to explain it when you just have to accept it as a fact. Joules is the amount of energy per velocity over a mole of a certain amount of substance per every degree Kelvin. One more time. The mass and the velocity of a substance of 1 mole for every degree Kelvin. So the unit of joules broken down is this. The mass times the velocity of 1 mole of a substance for every 1 degree Kelvin. So joule, in its written out derived unit, is kilograms times meters per second squared divided by mole times Kelvin. Again, this whole thing is represented by the letter J. This is a new topic. This is something that's brand new. So this goes back to why, just a minute ago, that when I did the root mean squared, I did 3, and again, R is joules per mole, that's the unit, times Kelvin, which is times Kelvin, over kilograms per mole. So your question is probably going to come from, well, then why is the unit, you told me this earlier, meters per second? Well, if you will look, the joule on top was meters per second squared times kilograms. Well, now let's look at all of our units. Kilograms will cancel, moles will cancel, K will cancel, and that leaves us with meters per second squared. Well, then how do we get from meters per second squared to meters per second? Well, hopefully you've already seen the fact that we're going to take the square root of this thing. So hopefully that did not confuse you. So let me tell you one more time. We know that the R unit is joules per mole. Well, we know a joule is kilograms per meters per second squared over mole. And again, this is your R value. Then it's times T, which is Kelvin. And then on the bottom, remember, and again, we have a 3 up here. We have the square root. I gave you the unit of the molar mass at kilograms per mole. And you know the unit for this thing is equal to meters per second. And again, there's your answer down there. So it is kilograms canceled, moles canceled, Kelvin canceled, leaving you with meters per second squared. And then again, how do you go from meters per second squared to meters per second? Again, it is the fact that you take the square root of this mass. All right, so hopefully, again, that makes sense. If we could monitor the path of a single molecule, it would be very erratic, which means the mean free path. Well, you definitely know what mean is, hopefully, by this point. You've been in enough math classes, you know what that means. Mean is simply the average. So it's the average of how it travels. Okay? So the average distance a particle travels between collisions. Now, you've got to remember, these are molecules. Really, really, really tiny. It is a tenth of a micrometer. And a micrometer is 1 times 10 to the negative 6. And it's a tenth of that. So really, what we're talking about is 1 times 10 to the negative 7th power. Really, 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 really tiny. All right. Heat them up, speed them up. You know this. Examine the effects of temperature on the number of molecules. Of course, you heat them up, you speed them up with a given velocity. Drop a vertical line from the peak of each of the 3 bell curves. The x-axis represents the average velocity of the sample. Now, this is what I was talking about. This is a graph called the Maxwell-Boltzmann graphs. the first thing you have to understand is what's down here in yellow. These are 3 different curves at 3 obviously different temperatures. One more time, 3 different curves, 3 different temperatures. However, every curve has the exact same area underneath it. So in terms of how much space these curves take up, they're all identical. None of them have different amounts of area. So what does this mean? This is what I'm trying to get you to understand, and you will definitely see this graph somewhere on the AP exam. Somewhere. And this is kind of how I want you to understand it. So what I'm going to do is I'm going to play a hypothetical game for just a second. I'm going to use this line right here as my EA. And some of you may not know what EA is. EA is your activation energy. It's the amount of energy required to do, amount of energy required to get a reaction going. All right, activation energy to get a reaction going. All right, so this is kind of the way I want to explain it. The blue line, notice what it is. This is the lowest temp. Down here is our highest temp. So the first correlation that I want you to make is what happens to the size of the hill as you go from low to high. Well, hopefully you recognize as your temperature increases, the size of your hill decreases. That's interesting. It's backwards from what you would think. This is why students get confused. They see the tallest hill and they say that's got to be the highest temperature. Not true for Maxwell Boltzmann's graphs. Please don't confuse that. The lower the hill, the higher the temperature. So what does that mean for us? What does that have any effect with this graph? Well, let's look at this. Relative number of molecules with given velocity. So basically what we're saying is that the number of molecules have the velocities, which is down here at the x-axis, are underneath the hill. So most of the molecules in the high peak, the 273, have a velocity of about, let's say 500, okay, because it's about halfway between 1,000 and 0. So we're going to say they're about 5,000 meters per second. All right, so again, and then about half of the middle graph is almost 1,000, and about half of the average, I guess you would say, of the highest peak is, you're looking at around 1,500 to 1,400, okay? So that's what we're getting at. But here's the whole purpose of what I'm trying to get you to understand. We want to identify the highest temperature based on the shape or just the lowest temperature. Because some of the questions they could ask you is which one of these peaks has the highest temperature, and they may not show you these. You just got to understand that the highest temperature is the lowest graph. So here's the way to remember these. Let's pretend that this line, again, is your activation energy. And let's pretend that this line right here is the 3 on the AP exam. Remember, 3 is a qualifying score. So if we use the blue graph, okay, the lowest temperature, let's pretend that this is before school ever began. And if you are past this blue line, that means you're going to score a 3 or more or higher on the exam. So if you notice the highest graph, there is very, very, very few people beyond that point. Again, remember, this is before school ever began. All right. Well, then let's look at the next graph. We're about midways through the year. We've increased our temperature. We've increased our energy. I've energized you. I've got you some knowledge. I've taught you some content. Well, notice what has just happened. Our 3 line has drastically transformed into a lot more of the percentage beyond that 3 line. That's a good thing. So if you notice, we have more people beyond our activation energy. So we have more of a chance of a reaction to occur at this point. And finally, what if we get to the very end of the year, we're reviewing, I've taught you every piece of concept you could possibly know, and we still have this line right here that's our 3 mark. Now, if you've worked hard, you've learned, you've listened, you paid attention, look at the percentage of students who are beyond that 3 line. It has drastically changed from way up here when almost all of my students had no ability to make a 3. So that's kind of the way you can understand this. You put some energy in, you put some effort in, and the chances of you getting past this desirable line drastically increases, and you have more people that are doing it. That is Maxwell Boltzmann. Please do not confuse that graph. It's too easy to get it confused. All right, the last topic of this entire chapter, we're almost done, guys. Okay, let's just kind of work with me. Graham's law of diffusion and diffusion. Real quick, hopefully you should remember this from previous topics. Effusion, forced out of a tiny opening. Okay, it has to be under pressure to be able to do this. Under pressure, and then hopefully you know what diffusion is. That is simply a mixing of gases. All right, same exact thing, diffusion, mixing of gases. So if you'll kind of look at the drawing, notice there's a partition. They are bouncing off these partitions. They're not mixing, and then notice what happens. As soon as we take away the divider, you've got some red moving over here, some gray moving over here, so you have a mixture of gases. Effusion, the passage of, again, through a tiny orifice. Now, this is something really important. The rate of effusion measures the speed at which the gas transferred into the chamber. Remember, rate and speed are one and the same here. Important facts about effusion. The rates of effusion of two gases are inversely proportional. The rates of effusion of two gases are inversely proportional, which means as one goes up, the other goes down, to the square roots of their molar masses. What in the world does that mean? All that means is that heavier gases effuse slower. So if you have me trying to fit out of a little bitty tiny hole compared to a 4-year-old, there is a much greater chance of that child getting out of a tiny hole much faster than me. So again, there's one other important thing to remember. Remember, rate is a change in quantity over time, not just how fast. So we need to talk about how much exits, not just how fast it exits. All right, and here is your formula, and there's something very important that I want you to grasp. Notice the first thing is that the rate of diffusion, again, the rate will be a number. It will be a number. The rate for gas 1, and notice where the 1 is over here. It goes to the opposite side. The rate, again, will be a number for gas 2, and notice where it goes. It goes to the top. And then I give you a little hint. Always put the heavier gas on top. Why would we do that? Because if you put the heavier gas on bottom, and when I say on top, I am specifically referring to the mathematical aspect of this, the square root version. Because if you try to put the molar mass, oh, my apologies, I need to state this. M stands for the molar mass. My apologies, I did need to make sure you knew that. Okay, M is the molar mass. So why don't we put the higher one on top? Well, if you put it on bottom, you're going to end up with a fraction or a decimal. That does us no good. That does us no good. So make sure you put the heavier gas on top. So calculate the ratio of diffusion rates of hydrogen gas, H2, with uranium hexafluoride, a gas used in enrichment for nuclear cells. All right? So let's look at that. Remember, the rate of 1, rate 1 over rate 2, and again, it's going to come out to be a ratio, is equal to the square root of the molar mass of 2 over the square root of the molar mass of 1. Now, which one of these is heavier? Well, obviously, uranium is going to be heavier, so I'm going to put it on top, and I'm going to put it over the square root of hydrogen, which we know is 2.02. And if you look up the molar mass of UF6, it is 352. Now, there's a little thing that I also want to mention while we're at it. Do you have to do the square root of that number, divide by the square root of the bottom number? No. Hopefully you know your mathematical properties, that you can take the square root of the entire function, and it be the exact same. And the answer that if you do this, you should come out with is 13.3. So what is my whole purpose of doing this? What we now have determined is, the first question is which one was lighter? Hydrogen is. So does that mean it's faster or slower? The lighter the lighter the faster, the heavier the slower. So what we're saying is that hydrogen is 13 times faster than UF6. That's why we put the heavier mass on top. One more time. So hydrogen is 13.3 times faster than UF6. All right, so hopefully that does make sense. All right, a compound diffuses through a porous cylinder 3.2 times faster than helium. What's its molar mass? All right, well, this time we're going to kind of have to work it a little bit backwards. We know that the rate is 3, apologies, let's try this again. We know that the rate is 3.2, and again, the compound diffuses through a porous 3.2 times faster than helium. So that means helium is the heavier gas, so it has to be on top. All right, so let me try this again. Let's erase this. So helium has to be on top, and it's the square root of its mass. And the molar mass of helium is actually, it's 4. And then we have the square root, essentially, of x, because we're trying to determine it. So you would take the square root of 4, and then you would multiply the square root of x by both sides, and then you're going to get, so essentially it is the square root of x equals 2 times 3.2. So multiply those two together, and then take the and then square both sides, and you'll get your answer. Okay, so that is how you would have to do that one. All right, so I don't want to take up too much more time, but so we're going to kind of move on from here. All right, again, you can probably figure this one out. Which gas would effuse faster? And I'm not going to answer this. I want you to figure out. Effuse faster means lighter. And then I will let you figure that one out. Now, this time we have Graham's law of diffusion. Well, this kind of looks really familiar. Last time it was the rate of effusion over 1 over 2. But notice the difference. Remember, what does diffusion mean? Diffusion means to mix or to spread out. So it's the distance traveled. So imagine someone standing at the front of the classroom, spraying an air freshener, and then how long and how far did it travel? Well, let's think about that. Distance traveled. If you are 400 pounds and you're trying to race someone who is 160, who's probably going to run further? Well, hopefully you said the lighter one will run further. So that is also applicable here. So the distance traveled, the heavier gas goes on top. Again, this still stands for molar mass. Okay, and the heavier one will travel less. Okay, so heavier travels less distance. The heavier gas travels less distance. All right. Now, this is also a question that's really, really, really important, and I love this question in terms of what it presents to us. All right, let me go back. This question I really want to spend a good deal of time on, and so this may extend the video just a little bit, but it's really imperative that you get it. Okay. So what we're going to do is we're going to take the mass of NH3, okay, which is about 17. And then we're going to take the mass of hydrogen chloride gas, all right, and which is a mass of about 36. And what we're going to do is we're going to take those two gases and we're going to have a wet cotton ball of NH3 and we're going to put it on this end. And then we're going to have a wet hydrochloric acid solution and we're going to put it on this end. Now, again, these molecules definitely have an aroma. They have a gaseous state to them. And so what we're doing is we're essentially mixing these gases in terms of, they're going to basically meet in this tube. But here's the interesting part. The first thing that I need you to get is that a white ring of NH4Cl forms. So let's talk about that. Well, we know that NH3 plus HCl is essentially going to create NH4Cl plus H2. Right. That's what we're going to get here. This is our reaction. Now, So what does that have anything to do with anything? Well, notice what it has right here. NH4Cl is a solid, and it shows up as like a little white smoke ring. So here's our smoke ring. What's important about that? What I want you to see, and again, let me show you, the mass was 17, the mass was 35. If I were to draw a line basically almost down the center of this tube, we're looking somewhere about right here. Well, what do you notice about where that ring formed? It definitely did not form at the center. Well, why did it not form? Wouldn't you think that these molecules would come out and go, and they'd come out and they'd meet in the middle? You would think that. However, it's not how it occurs, and this lab actually proves it. So here's what we're trying to understand. Again, mass is 17, mass is 35. What did I just tell you on the last slide? Heavier is slower. Heavier is slower. So these molecules don't travel near as far as these will, since these are lighter. That is what I'm trying to get you to understand. All right, so if we do 35, and again, we're doing the heavier mass on top. Let me actually grab my calculator and do it correctly. It's actually 36.36, if you want to do the math correctly. It is 36.36 divided by 17.03. And that is going to give me about a ratio of 2.1. So ammonia will travel 2.1 times as far. And again, the way we did it was 36. Oh, my apologies. I actually need to take the square root of this number. So let me do this. That is not right. It's actually, let's try this again, farther. One more time. 36.36. Again, square root of all that divided by 17.03 comes up to be a 1.5 farther. And again, which one's going to go farther and why? NH3, because it is lighter. All right, so that is what's going to be your answer. But let's look at something where kind of, let me backtrack. Let's start here. So what if we took two gases, and again, I'm going to change these gases because I don't know the real explanation to these. I don't know the real mass. I'm just going to make up. What if we make up something that's 26 grams per mole, and this one is, let's just say, 26.3 grams per mole? Well, they're the almost equivalent mass. So if we drew a straight line down the middle, where would you expect those to meet? Well, you would expect them to meet in the middle. That's exactly right. So the closer the masses are together, the closer they will meet in the middle. All right. So again, if it's heavier, it's going to be a lot slower. If it's lighter, it's going to be a lot faster, and that will determine how far down the tube they will meet. All right. The observed ratio is less. And again, what does that say? The observed ratio, not the mathematical ratio. We determined it to be 1.5, but when you actually measure it, it's less. And the question is why. Now, this diffusion is slow considering the molecular velocities are 450 and 660. Now, and then I kind of propose this question. Which one is which? Well, we know lighter travels faster, so the 660 must be the NH3, and the 450 must be the HCl because it is heavier. This tube contains air. Now, what in the world are you talking about air? Well, if you trap something in a tube, it's going to have air. There's no way to get all of that air out. So we have nitrogen in there, we have oxygen in there, we have hydrogen in there, we have carbon dioxide in there. So all of those gas molecules are in this tube along with the NH3 and the HCl. So what does that mean? Well, essentially there's things in the way. So if we have a package or something at the front of the school and I asked you to go run to it between classes or during break, well, obviously you will get there much faster than during class than you would during break, because the collisions are going to slow the process. So again, hopefully that makes sense to you. So an observed ratio will be less because this is real world, but if you could remove all of the air contents out, you would be much better. All right. Again, if you want to go back and look up these YouTube videos, again, they're pretty interesting. Again, I don't have the ability to pull those up at this time. All right, last few slides. Almost done, guys. Why do real gases not behave like ideal gases? And we've already talked about this. Number one, real gases have attractive forces. Another way, what we're saying here is we have IMFs. Real gases have a finite volume, which means you can calculate it. And there's one more that I want you to add, please, and that is no elastic collisions. That's another one. No elastic collisions. All right? And how do I make a real gas behave like an ideal gas? And this is kind of way, remember, ideal things are perfect. And the way I want you to think about perfect is if you could describe your perfect summer, what would you describe? Well, the first thing you're probably going to say is hot. The second thing you're probably going to say is no job. And the third thing you're probably going to say is no chores. Well, if I'm explaining that in terms of chemistry, well, I would say you got high temps. So again, let's read this one more time. How do I make a real gas, a real person, have a perfect summer, an ideal gas? Well, I'm going to heat them up. You don't want a cold summer. And also, if you have no job and you have no chores, that means you have no stress, no pressure on you. You can do whatever you want. You can go to the beach all day, every day. So again, that's what you're going to do. You decrease the pressure, you get rid of all the outside influences, and you increase the pressure. Now, why does that work? That is going to be something that I kind of want you to think about and go through. Now, I'm going to be honest with you, I'm just going to skip this slide, but here's the real reason why we have this ability to turn it to from a real gas to an ideal gas, and it's just called this van der Waals equation. I have never seen this formula ever enacted upon anything in AP. So essentially, it's a waste. But I just kind of wanted to show you that the way we can correct for high pressures and low temperatures, which would be a terrible summer, which means it's cold all summer and you got a job every day. You don't want those things. So we can correct for certain situations, okay? All right, and again, the final thing, let's look at this. Most gases behave ideally until you reach high pressures, low temps. Bad summer. So here's what we're going to look at. Notice what we have. This is your pressure, and this straight line is an ideal gas. All right, and this is your Pivnert value over here, okay? So if you notice, as pressure increases, again, job all day. Notice what they do from the ideal gas. They drop, and all of a sudden they shoot up. So from the beginning, at no pressure, everything's pretty ideal, right? Notice that one more time. At no pressure, everything is pretty ideal. But as you increase pressure, everything seems to get farther and farther and farther away from the pressure. Now, when Pivnert is equal to 1, the gases are ideal. Notice what it said. When Pivnert is equal to 1, the gases are ideal. Because all of these are at 200 Kelvin. That's one other fact. All right, the very last thing I want you to understand is that this graph right here is just for nitrogen. All right, just for nitrogen. Note that the non-ideal behavior is evident through each temperature. And then if you'll notice, the ideal gas at 1 atm likes to stay real even. But as every time your temperature changes, you're going to get a change in how ideally it works. Okay? And the last slide. Don't underestimate the power of understanding these graphs. Again, go back and look at them one more time. The AP exam loves to ask questions comparing the behavior of ideal and real gases. It's not likely you'll be asked an entire free response problem. One more time, let's get that. It's not likely you'll be asked an entire free response gas problem. Gas laws are tested extensively in the multiple choice. Since it's easy to write questions involving them, you will most likely see Pivnert guaranteed somewhere in a free response problem. But again, it won't be the whole problem. All right, so again, hopefully this chapter was easy. Hopefully you got a lot out of it. There are some free response questions that I would like to go over, and that will be in a totally separate set of recordings and probably some classwork that we would have time to get into. So thank you again for watching all 5 of these recordings, and I hope you've had a wonderful time watching them, and have a great day.